Okay, so I just wanted to finish up this one problem we were doing in class just to make sure that it's clear. First of all, we were trying to get the inverse of this matrix, and we found out that it was singular, and I just didn't completely, I just kind of explained why it was singular, but I didn't finish wrapping it up. So this is what we already did in class. We were just trying to get the left side of this matrix to look like the identity matrix, because that's how we find the inverse of a matrix, is to set it up this way where you have the identity matrix on the right, and then you use row operations to get the left side to look like the identity. So really, at this point, you can tell that it's going to be singular because the rows 2 and 3 have the same coefficients on the left side, but I'm going to show you why that is. So the next step you would naturally do here would be to try to get a 1 in the second row, second column. So you could multiply the second column by -1/3, and that would give you these. So the next thing you would do would be to try to get rid of that -3 that's under the 1 that you just got in the second row. And one way you could do that would be to just subtract row 2 minus row 3 the way they were in the previous matrix. And so when you do that, you can see that you get all zeros there on the left side. And so you're never going to be able to get a 1 in the lower right, because there's just no way to do it without messing up your other rows. So that is why this ends up being singular. It does not have an inverse. Okay, so moving on, there is a formula for the inverse of a 2 by 2 matrix, because if you were to set up ABCD, you would set it up the same way that you set up any problem where you're trying to find the inverse of a matrix. And this is just the derivation of the formula. This is not me doing this problem. So that's where the formula comes from. And then in this problem, you just want to take this matrix 2, 9, 1, 5 and find the inverse by using the formula. So you just plug in 2 for A, 9 for B, 1 for C, and 5 for D, and you get this for the inverse. And 1 over 10 minus 9 is just 1. So the inverse is 5, -9, -1, 2. So that's how you use that formula. I'm not going to ask you to memorize that formula, because you can always find the inverse of the function, the inverse of the matrix in the normal way. All right, so solving a system of equations using the inverse of a matrix. This is just like in algebra, how you would solve for x. So you have this system of 3 equations and 3 unknowns. You can write the coefficient matrix, which is just the coefficients of x, y, and z, and multiplying the coefficient matrix by the matrix x, y, z gives you that whole matrix, the left side of the equal signs, and then on the right side of the equals, you've got the constant matrix. So this, if you look at this as just an equation, AX equals B, where A is the coefficient matrix, X is the matrix X, Y, Z, and B is the matrix of the constants in that system of equations, then if you were just looking at this as an equation, the way you would solve it would be to multiply both sides by the inverse of A, or 1 over A is how it would be if you were just using real numbers. But in matrix algebra, it would be multiplying it by the inverse of A. Then the inverse of A and A would cancel, and you'd have X equals B times A inverse. So if you find the inverse of the coefficient matrix and multiply that by the constant matrix, you will get the solution XYZ for the system of equations. In situations where matrix A does not have an inverse, this won't work, but it is a method of solving 3 equations and 3 unknowns. And whether it's easier or harder than doing it the normal way, I don't think it's easier, but it's just a kind of an exercise. When we learn Cramer's rule, which we will learn in the next lesson next week, you will see really the best way to solve a system of equations like this, but we'll do it as an exercise. Okay, so we're going to use the inverse of the coefficient matrix to solve this system of equations. We already found the inverse of this matrix in an earlier example, so I'm not going to do the whole thing again. But if we look at this system of equations, the coefficient matrix is 1, 3, 0, because there's no z in that first equation, 1, 1, negative 2, and negative 3, negative 3, 5. The variable matrix is x, y, z. Those are our variables. And the constants are negative 10, negative 4, and 11. So you've got A, which is your coefficient matrix, times the variable matrix equals the constant matrix. And now we're going to multiply both sides of that equation by A inverse. So multiply the constant matrix by the inverse of A, which we already found before, and you will get your variables, your answers, your solutions to that system of equations. So here's the inverse we found in the earlier example, and we're going to multiply that by the constant matrix. So that will give us this matrix, and when you add that all up, you get your x, your y, and your z, and you can see if you just plug it in that it will work in the equations.